what we're doing now is, next thing, I'm going through a phase of showing you how to complete calculations. We've sort of initiated you into the high priesthood. You know, I can give you now a Lagrangian, and you can, in principle, read off from that the Fineman rules, tell me what's in the theory. Now, admittedly, you get a little better, more confident about doing that after a lot of practice. But basically, the rules for reading a Lagrangian are pretty simple. Okay, so let's just go over them quickly. So when we're doing the Fineman rules, we have a set of vertices. It's basically a bunch of vertices and propagators. And to get a vertex, all you do is you take the interaction Hamiltonian, but minus I, and you take its matrix element. Okay, or that's equal to the same thing as plus I, the interaction Lagrangian. So given a Lagrangian, you put a factor of I in front of it, and you take its matrix element, and then to get the vertices, you drop the external stuff. All right, I'll even call it stuff. Okay, so what does that mean? You drop the e to the minus I p dot x pieces, the plane wave parts. Okay, you drop the 1 over the square root of 2 omegas that appear. If there's a photon around, you drop the epsilon mu, and if it's a fermion around, you drop the u's. V or V's. Okay, some of these get added in later. So this guy, the e to the I p dot x, turns into the 2 pi to the 4 delta 4 of p initial minus p final. So overall momentum conservation. So that's where that guy goes. The 1 over 2 omegas go into 1 over the square root of 2 omegas in the transition matrix element, and then there's an minus I m. So those guys just get pulled outside. That's why you drop them, and these guys get added in as part of the Fineman rules if you have an external state. Okay, so well, I want to do examples before moving on. Let's do some examples. But anyone have questions about the rules? That's basically what there is to doing rules. You get those factors for all the vertices. Anytime there's a line drawn in between it, there's a propagator, you put a propagator in there. And then there's a few little fussy rules like -1 for a closed fermion loop and things like that, which you either work out or look up. Okay? So the last time I did Compton scattering. So let's remind you of what I did there. So Compton scattering. Okay, and that's basically a photon on the target, whatever your target is, goes to a scattered photon plus a scattered target. Okay, and we did the boson case, and let's just step through it again. For bosons, the Lagrangian is, it's d mu phi star, d mu phi. That's maybe a mass term, phi star phi, things like that, plus anything else you wanted to add in. But we're doing the QED part. And so photons live in those covariant derivatives. So this looks like there's the usual pieces, d mu phi star, d mu phi. Then there's minus m squared phi star phi. So that piece tells you that it's a scalar particle that in principle defines the propagator. The next piece that you get is the minus a mu j mu piece. So if there's a charge E, it's a mu, and it was I d mu left minus right phi. That was the current. This is the j mu. Probably with the E included in the normal definition. And then there's the piece E squared a mu phi star phi. I think I snuck the I in there. There it is, right there, right there. Okay, I snuck it in. Okay, and I think I have the sign right too. Okay, okay, good, thanks. Okay, so we know how to take these matrix elements. We've done this a few times now. These derivatives turns into p's, and so this vertex turns into a matrix element. If I write this out, this guy is minus I e times P1 plus P2. So here's P1, P2, mu. So we've taken the matrix element, the derivatives turned into momenta. We've taken IL, so it's minus IE, and we've dropped the external photon epsilon, and we've dropped all the 1 over 2 omegas. So that's how we did that matrix element. This matrix element here would be something that has 2 photons in it, and that's 2e squared with an I, g mu nu, and that's it. Okay, what we've done is we've written this as g mu nu, a mu, a nu, and we've dropped all the external states, and the factor of 2 is a counting factor because there's, one of these annihilates the initial one, and that's the final. And there's 2 choices for that. Okay? And okay, I think that's right. And so then we wrote out the matrix element. The matrix element, there were 3 diagrams to get there. There's, forget it, I'll just use it as a separate page. Come on, there we go. So for the matrix element, we have a process like that. So P1, K1, P2, K2. We label this P1 plus K1. There's another possible diagram where the initial photon comes in and hits the second guy, the second vertex. This then is P1 minus K2, the intermediate state there. That's K2 coming out. And the fact that they cross, they're not interacting, they don't, going past each other, they just have to be drawn that way. And then the third diagram comes from the vertex there. Like that. Okay. So the matrix elements, I'll just write it out. We did it last time. I'm happy to take questions, but I will write it out here all together. Okay, minus IM. Okay. There'll be an, since they're external states, there'll be an epsilon. If this guy carries index mu, that guy carries nu. Epsilon mu of K1, epsilon star nu of K2. Okay, so those are the external stuff that you stick back at the end. And then we have a couple diagrams. If I write them right underneath each other, the last one's easy to write. It's plus 2I g mu nu. And I missed the factor of E squared. E squared. There we go. Okay, let me divide that up in half and try to squeeze the first diagram into the first part there. Okay. The first diagram, if I'm reading from this side here, I come in, I hit a vertex there with P and P1 plus K there. So this turns into minus IE 2P1 plus K1, and that's the connected up to mu. Yeah, it should be. Okay. Then there's a propagator, I over P1 plus K1 minus M squared. And then there's the other line, minus IE 2P2 plus K2 nu. Okay. I've used the fact that P1 plus K1 is P2 plus K2. And the vertex rule was the sum of the two momentums. So here was, first I wrote here P1 plus K1. Here I wrote P2 plus K2 plus P2. So those are those factors. Okay, and then the second one, let's just write it out quickly. Minus IE over on this side here. The first thing that happens is the final one, so it's 2P1 minus K2 nu. I over P1 minus K2 squared minus M squared minus IE. This is P2 minus K1. So it's 2P2 minus K1 mu. Okay. So the features here that people, novices, often miss are that the Lorentz indices mu and nu go along with the photons, so the currents that couple to this carry that index. So for example, in the first case, here was the current for the initial photon. So that had the index mu, and then the second case was this one over here, which lives right there. Okay, anybody have questions about that? Is that mysterious or is it too obvious? Okay, it could be either extreme. I'm trying to be neither. Okay, here, in this case, I've written them in a given order is not important here. Okay, and the reason is that these are just numbers. Okay, these aren't matrices or anything, you know. So if I can reverse the numbers, it doesn't make any difference. But I wrote them in this order because the next example I'm going to do, the order is crucial. And if you, the typical novice thing to do is to write them in the wrong order. And so by writing them in this order, in this case, I've tried to build up the habit for that. As you see from the diagrams, the way I wrote them, we have this unfortunate habit of drawing pictures where the initial states in the pictures live off to the left and the final states live to the right. But when we write formulas, quantum mechanics formulas has the initial state over here and the final state over on the left. So the thing to think about when you're writing the rules out is that over on this side here is the starting state, and you write it backwards from the picture. Okay. Life. Okay. And that's important in the next case. So the next case is going to be two fermions. Okay. So here the Lagrangian is the fermion piece is ID slash minus m psi, and you write that out as the kinetic energy piece, which determines the propagator, minus the interaction piece, E a mu psi bar gamma mu psi. Okay. So the Feynman rule that comes out of that, if you take the initial state going to final state, I take that vertex, I throw off all the external stuff, which is all the spinors and the photons, and I'm left with plus IL, which is minus IE gamma mu. Okay, so you look at this and you say minus IE gamma mu. Okay, that's what you do. Okay, so here there's only this one vertex instead of the two that we had in the other case. And so when we write out the diagrams, there's actually only two diagrams instead of three. The diagrams are that plus that guy. And I don't need to label it, everything's the same. There's no third diagram. Okay, and that's a bit funny. You know, but it's what it is. And the Fineman rules for this are minus Im equals. Okay, so again we have the epsilon 1 mu epsilon 2 star nu sitting out in front on that side, just like above. And that means the same thing, means of K1 and K2. Okay. But now the internal stuff is different. The Fineman rule tells us, again, we're coming in from the right. This guy's the mu, so it's minus IE gamma mu. Then there's a propagator, I over, this was P1 plus K1 slash minus M. And then the second piece is minus IE gamma nu. And so those are the factors there. And then the second one is coming from early. I first hit the outgoing photon, so that's a nu. So it's minus IE gamma nu. The propagator, the momentum was P1 slash minus K2 slash minus M, and minus IE gamma mu sits there. Okay, and then not very cleverly, I didn't leave room for my external spinners, because these guys are matrices. To turn this into a number, there's a U of P over here, and a U bar of P over there. That one's P2, this is P1. All right, so I'm sorry, I didn't do a good job of leaving spaces there. Okay, so you throw away all the external stuff when you start, you get your rules, then for your external state you put it back in. Here's the external state, the incoming external state U of P1, the outgoing U bar. Here's the photons, and here's all the stuff in between. This is now a number, because that's a column, that's a column vector, a row vector, and this is a matrix, so that's just a single matrix element. It's a very complicated number, but it's what it is. And these guys are matrices, and so here the order was extremely important. Okay. The matrices don't, in general, commute. So here the typical novice thing to do is to write these in, with U bar sitting inside here, or basically not paying attention to matrix indices. Okay, so that's the thing to avoid. Okay, anyone have a question about how one does that? So that's applying the Feynman rules. Yeah? All right. Actually, one of the remarkable things to say is that at the non-relativistic limit here, both of these are the same. Okay, and that's a bit of a surprise. I'm not going to go through it and show it, but if you take the low momentum limit of this guy and the low momentum limit of the one above, they're the same, and you can argue that should be the case from general principles. It's basically that the spin doesn't play any role in low energy scattering. If you do the non-relativistic limit, you get the Schrodinger equation in both cases, and the Schrodinger equation's result for Compton scattering is well known. Okay, so it reduces to the Schrodinger result. Looks a little fancy, but that's what it is. Okay. Okay, there's us reading a Lagrangian and writing out matrix elements. Okay, the next thing that we do, if there's no questions, is okay, I'm starting a unit which I'm calling calculating. Okay, and it's basically the rest of the process. So the things that we're going to do decay rates, we're going to do cross sections. Okay, if you just think of what we just did there, we wrote out the matrix element, but we haven't got anything observable yet. We don't know. You square the matrix element and do something, but what do you do? So today we will find out what you do to complete that calculation. There's a couple other things that I stick into this unit just is I'm going to talk about identifying symmetries and currents, we're going to complete the process of what we did on ground state energies. I've prefigured this by a couple of these homework problems and talk about, you know, reading off masses. I'll call it excitation energies. Okay, so these are the sort of the last tidbits of our basic development. Okay, but the big guys, the really important ones are these two here, decay rates and cross sections. Okay, and let me give you the answers. Decay rates and cross sections. Okay. Here's what you get. Then if I have some particle decaying to two particles, let me just give you this guy first. Okay. It's a long formula. It's 1 over 2 times the mass of the particle A. Integral d3 pb 2 pi cubed 1 over 2 omega b d3 pc over 2 pi cubed 1 over 2 omega c. Okay. Then the matrix element squared, so there's our matrix element squared, and then 2 pi to the 4th delta 4 PA minus PB minus PC. Okay. So this breaks up into a bunch of pieces. There's overall energy momentum conservation, that's nice. Matrix element squared's nice. This combination there, d3p 2 pi cubed 2 omega c, 2 omega. Okay, this is referred to as Lorentz invariant phase space. Okay, and part of the goal today is to explain what that is. And the 2ma out in front is just a normalization in our conventions. Okay. The cross section is built of the same thing. So let's take A plus B goes to C plus D. Well, it's almost the same thing. It's one. Okay. There's some prefactors. Then there's the Lorentz. There's the phase space factors. PC over 2 pi cubed 1 over 2 omega C d3 PD 2 pi cubed 1 over 2 omega D. There's matrix element squared 2 pi to the 4th delta 4 of PA plus PB minus PC minus PD. Okay, so all that's pretty similar. That's exactly similar if you look at it. And then what comes out in front is a flux factor. Okay, so it's 2 omega A, 2 omega B, VA minus VB. Boom. Okay. Okay, so there's some factor there. Now, for fermions, wherever you see 1 over 2 omega or 1 over 2m, that goes to 1. Okay, that's just, again, our normalization convention. We could choose a normalization convention where that you don't have to say that, but it makes the start of the course tougher to explain. Okay, so that's what we got. Now, this is funny. In some books don't bother even explaining this or calculating it, and just give you the answer, as if it's supposed to be obvious. Okay, and other books go through a long and laborious derivation of it. I'm going to try something in between. Okay, both of these formulas are both basically Fermi's golden rule. In fancy dress. And so what I'm more interested in is that you understand, one, I know from experience that a lot of people are not that solid on Fermi's golden rule, so I'll review that. And then basically what I'm going to do is I'm going to show you why it's Fermi's golden rule, so that if you understand Fermi's golden rule, you'll feel comfortable with this stuff. Okay? Basically, you can get both of these from rates. Fermi's golden rule tells you how, when you have a transition amplitude, you turn that into a rate. That's what the Fermi's golden rule is. So m squared goes to rates. Okay, and this is a rate. Okay, it's a decay rate, so you might expect it's Fermi's golden rule. And this one you can get as a rate. You know, you set some flux in, and what's the rate of stuff coming out. So cross-section's gotten by dividing the rate out by the flux in. That's why there's a flux factor here, and a rate up on top. So with that in mind, let's go back to a quick and dirty derivation of Fermi's golden rule. Okay, so Fermi's golden rule comes from time-dependent perturbation theory. Okay, and it says V is some V0 e to the I omega t. Okay. That's the typical starting point. And then your amplitude. Let me call it the transition amplitude from the initial state to the final state is the integral from some t0 up to some t dt prime. The matrix element of v of t. So it's actually, I'll write it V0 e to the I omega t, initial, and then e to the I omega fi t. Okay, that omega fi is ef minus ei, and if h bars are there, that's divided by omega. Okay, so that's what you calculate, that's what you all memorize for your qualifying exam, etc. Okay. And this then turns into, in the long t limit, okay, so as you go for, if you just go for a little time, it's not this. But if you go for a long time, you take t0 to minus infinity, t to plus infinity, like we do in the scattering process. this turns into, f v0 times 2 pi delta of EF minus EI minus h bar omega. Okay, so there's a delta function there. Okay, so that's your long time limit. Okay. Then your probability for a transition is the amplitude squared, let's just call it V squared times 2 pi delta okay, so that's what you would get. Now, of course, it's hard to interpret the square of a delta function, so how do you do it? So here's where the quick and dirty part comes. Okay. To understand delta squared of the energies. Okay. How do you do that? Well, if I take one of them, I'm going to keep one of them floating around. That's floating. And then the other one is, delta E going to 0. Okay. So the other one is now evaluated as, what is that delta function? 2 pi times delta E of 0 is integral dt over all time, e to the minus I delta E t, delta E going to 0. And if I take that limit, it becomes the integral dt. It's just the total time t, which is going to infinity. Okay. So then Fermi's golden rule comes from the following. It says that the rate is the probability, divided by this big time, is 2 pi delta E final minus E initial V squared. VFI squared. Okay, now if you go to Merzbacher or whatever book you're using and look for a more rigorous or a better definition, it's a very fussy definition, because what you do is you take the long time limit, you show that the energy peaked around the energy conserving part, you massage it fancy ways, and you get out this factor of time and divide it out. But this is the quick and dirty derivation. That's Fermi's golden rule. Actually, you see Fermi's golden rule in two forms. There's two forms that you see, and it's important for us, the difference. Okay. One is the rate of I goes to F it's this factor we have 2 pi delta EI minus EF times VF I squared, the matrix element squared. And the second form that you get is 2 pi V squared times the density of final states. Okay. This is the density of final states. Okay. All right. So if if you're really calculating away, you always end up using this. So if I'm doing atomic decay of atomic state, so A in an excited state, atomic atom in an excited state decays to a final state, there's some density of final state factor. If I'm doing photoelectric effect, the final state in that case is not the photon going out, but the electron that's been kicked out. So I have a light in, kick out an electron. The density of final states is that of the electron. Okay. So that's the factor. What's the relation between these two? Okay. So sometimes you see the first form written as the definition of Fermi's golden rule, sometimes the second. Well, the relationship is that the density of final states is defined as the sum over all final states of states that satisfy the energy conservation condition. Okay? So basically, to get from this form to this form, you just add the sum over all possible final states that satisfy energy conservation. And that tells you what the density of final states is. I'll calculate it next, but that's its logic, okay? And if you think of it, you think of an atom here, the photon can go off that way, it can go off that way, it can go off this way. There's more than one final state that can occur. So you're summing over all of those. Okay? Well, how do we sum over all those? Well, there's a factor. And that factor is the integral d3 p, whatever p final is, p final, over 2 pi. It's actually 2 pi h bar cubed. I just put it in there just to see. That's the counting factor that tells us the density, what final states there are. EI minus EF. Okay, and if you're really fussy about it, let me put this in parentheses, dotted. There's a factor of the volume of space-time. So I'll come back and comment on this. Remember, if you count in statistical mechanics, there's one state for every 2 pi h bar in phase space. So d3x, d3p is your phase space. All right, so maybe I don't need to go do that. You should trust me on the factors of V. We can use box normalization and get these same results, but that's more painful than I care to do here. Okay, so basically we're trying to calculate how many states there are that satisfy energy conservation. So you sum over all possible ones, but you only keep those that satisfy it. Okay, so actually let me just do it. I'll do it for any mass particle. This you may have not seen this part here. All right, let's write d3p is some angular factor times p squared dp. I've got then 2 pi h bar. I'm going to carry my h bars around. They're in my notes, and if you do that, okay. I've got my delta E minus EF. Okay, at this stage, it's good to do the following. This is a trick that you'll have to use in field theory, so watch for this guy. Since E squared is P squared plus M squared in general, okay, this is true no matter whether you're relativistic, non-relativistic, etc. Then 2E dE is 2P dP. Okay. Since my delta function is a delta function of energies, I can change dP into dE and then just do the delta function. So it's integral d omega P E dE. Those are all labeled F. 2 pi h bar cubed delta EI minus EF. Okay, and you can do the delta function then. So then it's d omega P E over 2 pi h bar cubed. Okay. You might take d omega to 4 pi, but at this stage it's not completely clear. You know, your matrix element, your V, could depend on angle, for example. Let's imagine it did. So sometimes you leave it, sometimes you don't. But if you go back to your quantum books and you look at what you'd use for the decay, let's say atomic decay, the rate for atomic decay, your density of final state factor, this rho of E, it turns into, for photons, it's P squared, because E and P are the same, over h bar cubed, and the factor is 2 pi squared because you set d omegas to 4 pi. So that's what you use when you do atomic decay. If you do the photoelectric effect, so you do gamma, atom goes to atom prime plus an electron. The electron is the final guy, and then it turns into P times the mass over 2 pi squared h bar cubed, and I guess there's a c squared there. Okay. That's the factor you use for the photoelectric effect. They're both just the limits. The one's the relativistic limit, the other's the non-relativistic limit, but that's the general formula. Yes? It's EF. It's the final state. Okay, so you're summing over all. So you've got some fixed initial state, like an atom, and you're summing over all final states that satisfy it. That's what you should think of. Okay, so really, Fermi's golden rule, the rate should really be written in some combination of the two. It's d3p final, 2 pi cubed, the matrix element of v squared, 2 pi delta E initial minus E final. Okay, so that's the best version of Fermi's golden rule. You sum over all final states that satisfy it. Okay, and if you do box normalization, there might be factors of the volume floating around, but this is continuum normalization. Okay. Okay, so that's the guy that we're starting with. But I want to generalize this yet more. Okay. And to think about it, let's just apply it to, some excited atom state goes to another state plus a photon. Okay. And one of the things you'll see is that there's something asymmetric about what we do. Okay. So I'm doing non-relativistic quantum mechanics still. So the potential here, the interaction piece, is P dot A over M. Right? It came from P minus, now I need my factor of E. P minus EA over 2M squared. Okay, that's the piece that gives the transition amplitude. Okay, and so gamma of A star goes to A plus a photon, that's the rate, is by this rule integral D3 P gamma 2 pi cubed. We square the matrix element A gamma E P dot A over M A star initial squared and 2 pi delta E A minus E A prime minus E gamma. One star, okay? So that's what quantum mechanics would tell us to do here. But this is actually a very odd formula if you think about it. It's odd because I've got an atom in the final state and a photon in the final state, yet I only have the integral D3P gamma. So there's an asymmetry. Why do we have D3P gamma and not D3PA? Because there are other states also in the atomic states in the final state, and the reason is that the state A is actually fixed. This state of A is fixed by momentum conservation. Okay. And so in fact it's not needed to integrate over that. For every photon there's a unique atomic state. Okay? But let's restore the symmetry. So let's in field theory there's no distinction between this particle, that particle. They're all treated the same way. And so what I can do is I can write gamma is integral D3 P gamma over 2 pi cubed D3 PA over 2 pi cubed. I'll write 2 pi to the 4th delta 4 of PA minus P gamma times this matrix element V squared. Okay? now it's everything's explicit here. We've got this part symmetric. It doesn't, photons and atoms are treated the same. There's all of energy and momentum conservation. But I haven't really done anything. The integral d3 pa, the vector pa, over 2 pi cubed times 1 of the 2 pi cubes there, times the momentum part of that just gives 1. I've just added 1. Okay? So but this is now the better formula. This is the good formula. Okay? So we started off with this funny formula for Fermi's golden rule. We've made it look fancier, but this is really the real content that was always there to begin with. And then to get our final answer, when we've taken matrix elements of V, we've written this as 1 over all these normalization factors times the matrix element. Okay. So, well, actually, no bracket there. It's just a number. Okay. So we factored out all these guys. Is just to factor those out of the matrix element from what we call M, and then that gives us our final formula. Then gamma is 1 over, well, we're sitting in the rest frame, so it's 2 omegas, 2m, it's a star, integral d3 p gamma, 2 pi cubed, 1 over 2 omega gamma, d3 p, a over 2 pi cubed, 1 over 2 omega a, 2 pi to the 4th, delta 4 of pa minus pb minus p gamma, m squared. Okay, so there's our rate formula. It's really just the old Fermi's golden rule, just dressed up. So here's the sum over all possible final states. Here's energy and momentum conservation. These 2 omegas come out just because of our normalization choices, and that's the formula. Okay. Okay, so in a way, that's why some books don't even bother deriving it. It's something that you supposedly saw in quantum mechanics, except it gets dressed up in this fancy form. Okay, yes. So there's a normalization 2 omega a star here from the initial state, and we calculated decay rate in the rest frame of the particle. So 1 over 2 omega a star is 1 over 2 m a star in its rest frame. Okay, that's the reason for that. Thank you. Okay. Okay, so my first task is accomplished. I've got that. Okay, now let's go back and do the cross section. Okay, anyone ask anything about that? Let's do the cross section now. I'll try to. Okay. Now, the place where you've seen the cross section is when you do the Born approximation. You'd write d sigma d omega is some, you do f of theta squared. It's minus m over 2 pi integral d3 r e to the I. It's q dot r, but let me put it in p minus p prime here because that helps me v of r. Okay, that's often written as q, momentum transfer. Okay, so there's another formula that you've memorized for quals. That's it. When I teach quantum, I do this derivation two ways. Okay, one way is the waves on the pond. My derivation, I always give that, where you send some waves in, you have some target here, and you look at circular waves coming out. Okay, so you send waves in, they scatter off the thing, there's circular waves coming out, and that's one way to derive that formula. However, there's a second way, which is actually Fermi's golden rule, and I always do this way. I don't know if everybody does, but Fermi's golden rule. Okay. Okay. And it's basically the same idea. You have an initial state, a final state, and you want to use a rate. So here, my initial state is e to the I p initial dot r. My final state is e to the I p final dot r. So in other words, imagine I'm coming in with some plane wave and I'm observing it going out at some other plane wave. And my incoming flux is the magnitude of the momentum divided by the mass. So I'm not doing the whole derivation here. And to be honest, when I do it very carefully because I want to get the right answer. I do it in box normalization, so there's 1 over the square root of v there, square root of v there, and there's a 1 over v there, the v being the volume. So I do box normalization. So if you can see those ghostly volume factors, you can see it. But if you do that, then the cross-section is defined by the following. The cross-section is d sigma is the rate that you observe it by divided by the flux in. Okay. And that rate, so the rate is gotten from Fermi's golden rule, integral d3 p final over 2 pi cubed f v initial squared 2 pi delta E final minus E initial, and the flux factor is 1 over P over M. Okay, and for this density of final stage factor, I just do what we just did in my previous calculation. So I have 1 over P over M, P initial over M, times this guy turns into P M d omega over 2 pi squared. Okay. That's that piece I just calculated before by doing this delta function. The 2 pi squared is that. The PM was from doing the delta function. And then the transition amplitude is written as d3r, psi final, v of r, psi initial, d3x. I square that. And if you if you do momentum conservation here, so P initial and P final are the same thing. They cancel. There's an m squared. Bring it inside here. There's a 2 pi squared. You bring it inside there. This then turns into m inside, 2 pi inside the square, integral d3 x e to the I p initial minus p final dot x v of r. Okay. So that's the derivation of this cross section from Fermi's golden rule. If you've seen it, well, then you've got it refreshed, but that's how it goes. And again, I do it carefully with box normalization when I do it, but we got the answer correctly here. Okay, now in field theory, we want to generalize. Okay, what we had before, the scattering cross-section, you scatter off some potential, is really scattering off of another particle. So this could be an atom down there. It could be an electron scattering off of an atom. So we now write it in this form here, but you've got 2 final states. So you've got not only, let's make it an electron-atom scattering, you've not only got the final electron, but you've got the final atom. And so basically you go through the same steps. You take this formula up there and you generalize it to allow for the second particle in the final state, so just like we did before. So then d sigma is, well, I then have integral d3 p c over 2 pi cubed d3 pd, so this is over 2 pi cubed, 2 pi to the 4th matrix elements of v squared. And then the flux factor here was just the velocity. It turns into the generalization. This turns it to be VA minus VB. You know, the relative velocity. Okay, and that part I'm not deriving for you. Sorry. Okay, and then this turns into, when we take our normalization, you know, V is 1 over the square root of 2 omega 1 dot 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 m. It then 1 over 2 omega A, 2 omega B, VA minus VB. Integral d3 pd, 2 pi cubed, 1 over 2 omega d, d3 p c over 2 pi cubed, 1 over 2 omega c. The delta functions and then what we call the matrix element squared. All right. Okay, so what I will do when I come back is I'll take one of our calculations and carry out, get us to a cross section. We did the matrix element for scattering of 2 scalars and then the phi to the fourth, 6I lambda. I'll do all these factors out, and we'll come up with a nice concrete number. Along the way, that shows you how to deal with these factors, which I've sort of shown you how to do in that previous calculation today, but we'll do it again, and you'll get better at it. Okay. So that's where we're headed. We'll soon then be able to do all sorts of calculations. Okay. Any questions before we close up shop? All right, let's close up shop today. I'll see you Thursday.